The sun is the engine of our world, powering life, weather, and civilization. Its energy travels 93 million miles to reach us, but our access is limited. Solar panels capture sunlight, but only when the sun is shining. Clouds, storms, and night cut us off. Even on clear days, seasons and the sun's angle reduce what we can collect. We try to store energy in massive batteries, but this is costly and inefficient. Our civilization runs 24/7, but solar power is a part-time friend. We need more panels and land just to make up for cloudy days and long nights. Imagine trying to fill a pool with a hose that only works half the time. But what if we could collect sunlight where it never stops? In space, above the clouds and night, the sun shines constantly. There, solar collectors could work 24 hours a day, every day of the year. The idea is simple. Go where the sunlight is strongest and never-ending. Space offers a place with no clouds, storms, or seasons, just pure, relentless sunlight. If we want to truly harness the sun's power, we must look up. The solution isn't more panels on Earth, it's moving them to space. In orbit, the sun is a constant companion. The concept is profound. Collect energy where it's always available. This could transform how we power our world. The next step in solar energy is not on Earth but above it. To capture endless sunlight, we must go to space. The dream of capturing solar power in space began with the space age. In 1968, engineer Peter Glaser imagined giant satellites in orbit, collecting the sun's energy without interruption. He proposed placing these satellites in geostationary orbit, 22,000 miles above the equator, where they'd appear motionless in the sky. This orbit allows a satellite to beam energy to a fixed spot on Earth, day and night. These satellites would be covered in efficient solar cells, working almost constantly. The electricity they generate would be converted into microwaves for transmission. A focused microwave beam would be sent to a ground station called a rectenna. The rectenna, a vast field of tiny antennas, would convert microwaves back into electricity. This power would flow directly into our grid, providing clean energy, rain or shine. Glaser's vision was bold, a permanent man-made star delivering power from space. The technology was ambitious, but the roadmap was clear. The challenge was turning this vision into reality. Here's how a space solar power plant works. Sunlight hits solar panels on a satellite, generating electricity. Instead of wires, the electricity is converted into microwaves. A large antenna beams these microwaves down to Earth. The beam is wide and gentle, not a concentrated laser. Its intensity is similar to sunlight, safe for birds, planes, and people. On the ground, a rectenna, a mesh of small antennas, catches the microwaves. The rectenna converts the microwaves back into electricity for the grid. The structure is mostly transparent, so crops or animals can live beneath it. The process is efficient, safe, and scalable. No long extension cords, no dangerous rays, just a steady flow of energy. The key is converting and transmitting power with minimal loss. This technology could deliver clean electricity anywhere, anytime. It's a simple idea, made possible by modern engineering. Space-based solar power could change how we think about energy. For decades, space solar power was just a theory. That changed with Caltech's MAPLE experiment. In 2023, MAPLE launched a small prototype into orbit to test wireless power transmission. The device collected solar energy, converted it to microwaves, and beamed it to a receiver on the same satellite. Then, for the first time, it sent a tiny amount of energy down to Earth. The ground receiver detected the signal, a historic first. This proved that beaming power from space is possible. MAPLE showed the hardware can survive launch and operate in orbit. The experiment demonstrated precise targeting from space to a fixed point on Earth. It turned a half-century-old dream into reality. The core physics work. The next step is scaling up. MAPLE's success marks the dawn of practical space-based solar power. If the science works, why don't we have solar power satellites already? The answer: cost. Launching massive structures into orbit was once impossibly expensive. Traditional rockets made every pound cost tens of thousands of dollars. Building a city-sized satellite would have cost trillions. But now, reusable rockets like SpaceX's Starship are changing everything. Starship is the largest, most powerful rocket ever built, and it's designed to fly again and again. This slashes launch costs by 100-fold. Suddenly, launching thousands of tons is feasible. The price drops from trillions to billions, comparable to a major power plant. Starship could launch components for solar satellites in hundreds of flights. The dream is moving from fantasy to business plan. Cheap, heavy-lift rockets are the key to unlocking space-based solar power. The technology is ready. The economics are finally catching up. The door to limitless energy is opening. Beaming energy from space sounds risky, but the reality is safe by design. The microwave beam is wide and low intensity, less powerful than sunlight. You could stand in the beam and feel nothing. Multiple fail-safes ensure the system only transmits when perfectly aligned with the ground station. If the signal is lost, the power shuts off instantly. The beam can't be weaponized. It's locked to its target and spreads energy out, not in. The chosen frequency passes through the atmosphere and living tissue, harmlessly. Birds, planes, and people are unaffected. The system is passively safe. If anything goes wrong, it simply stops. It's more like a garden hose that shuts off when dropped than a dangerous ray. For Japan, space-based solar power is about energy security. With few natural resources, Japan relies on imported fossil fuels, making it vulnerable to global shocks. After the Fukushima disaster, the need for clean domestic energy became urgent. Japan's space agency, JAXA, leads the world in solar power satellite research. They've tested microwave transmission on the ground and plan to launch a demonstration satellite soon. Their goal, a full-scale, gigawatt-class power station in orbit by the 2040s. This would provide clean, reliable energy 24/7, free from imports and price swings. For Japan, it's about independence and a sustainable future. Investing in this technology is a national priority. The sky could soon be Japan's greatest energy resource. Space-based solar power isn't just for cities. It has immediate uses. The military could beam power to remote bases, eliminating risky fuel convoys. Mobile rectennas could provide clean electricity anywhere, saving lives and resources. Drones could be recharged in flight, staying aloft for months for surveillance or communications. Disaster zones could get power within hours, long before the grid is restored. The technology could support lunar or Martian exploration, beaming energy to rovers and habitats. These applications make power beaming a game-changer for defense, disaster relief, and space exploration. The first real-world uses may come sooner than we think. Space-based solar power is versatile, scalable, and ready for new frontiers. The future of energy is not just on Earth, it's everywhere we need it. Space-based solar power's main goal is clean energy, but it could also help cool the planet. Thousands of satellites would block a tiny fraction of sunlight, acting as a gentle sunshade. This could offset some global warming, a form of geoengineering built into our energy system. Unlike risky schemes, this approach is adjustable and secondary to its main purpose. When compared to nuclear fusion, space solar power uses proven technology, solar panels, satellites, and microwaves. Fusion remains a distant dream, but space solar power is within reach. The Caltech Maple experiment proved the concept works. The challenge now is scaling up and making it affordable. With reusable rockets, the final hurdle is falling. We may see commercial space solar plants before fusion reactors. Humanity's story is one of harnessing ever greater energy sources. Now we can tap the sun's full power, building a civilization free from pollution and scarcity. The question is, are we bold enough to seize this future? Would you live near a rectenna, knowing it powers your world with clean energy from space? The cosmos is waiting for our answer.